Colligative properties. Colligative properties are properties of solutions, and they are dependent on the number of solute particles dissolved in the solution. There are many types of colligative properties, but we're going to focus on two. Okay? The first one we're going to talk about is boiling point elevation. This means that the boiling point of a solution is higher than that of the pure solvent from which the solution was made. So for example, the boiling point of salt water is going to be higher than the boiling point of pure water. Okay? We're going to go through the reasons why. It's going to be written out in several different ways. So the attractive forces between the solvent and solute particles, those intermolecular forces, see how it's all coming together for this unit? So those attractive forces prevent the solvent particles from escaping to the gas phase, which is what boiling point, or what boiling is, going from liquid to gas phase. So we've increased the number of attractive forces. So it's like that solute kind of holds on to the solvent, preventing it from escaping to the gas phase. So in order to go to the gas phase, the solvent needs to have an increase in kinetic energy. And the way to do that is to increase the temperature. Okay? In order to overcome those attractive forces that it, the solvent, experiences between its own molecules and the solute that we dissolved in it. Okay? Let me give you an example. Is everyone done writing these words? Okay, let me give you an example. Water should boil at 100 degrees Celsius under standard pressure. Say you're ready to make some pasta. Okay, right? We did talk about this last class a little bit. You're ready to make some pasta, and you add some salt to the water, right? How many of you were ever told by, a parent, grandparent, family friend, family friend, Gordon Ramsay, somebody, I don't know if he actually would ever have made this mistake, but how many of you have ever been told that adding salt to water makes the water boil faster? Okay. That is incorrect. It's a misunderstanding. Adding salt to water does not make the water boil faster. It actually would take longer to boil because it has to reach a higher temperature. But now that it's boiling at a higher temperature, what's going to go faster? The cooking of the pasta. And it also is flavoring the pasta as it's cooking. Yeah? So water boils at 100 degrees Celsius normally. This means that the water molecules have enough kinetic energy to overcome those attractive forces, more specifically the hydrogen bonding between the water molecules. Once you add some sort of salt to it, for example, sodium chloride, that has KCl written here. That's what's in Seasonal, which is a substitute for people who can't do sodium because of like high blood pressure and stuff. But say you dissolve some KCl or sodium chloride, some sort of substance in there. The water is going to boil at a higher temperature than 100 degrees Celsius because those salt particles are attracted to the water, and so they're going to need more energy to convert to the gas phase. Okay. In order to make water boil faster, the best thing to do is what?
Don't watch it. Don't look at it.
Okay, yeah, a watch pot never boils. Yeah. Cranking up the temperature, I mean, it's not necessarily the best way to make it boil faster, or the best thing to do to make it boil faster. I would actually argue that putting in a larger pot would make it boil faster because it's more surface area. It depends on the amount of water. Like if it's the same amount of water in a smaller pot, it's going to take longer because they're more packed together and there's less, I feel like the more surface area for the bottom of the pot. But you're
Doesn't cold water boil faster?
Hot water freezes faster.
Yeah.
What's the fastest way to make something boil faster? Put a lid on it. It increases the vapor pressure in there. All right. So that's boiling point elevation. The other colligative property, the other colligative property that we're going to talk about and you need to be responsible for is freezing point depression. Freezing point depression. The freezing point of a solution is lower, it's been depressed, decreased, than that of the solvent from which it was made. A solid solvent, for example, ice, is a extremely organized, tightly packed arrangement of those particles. When you expose a substance that could potentially disrupt that pattern, or sorry, lead to the creation of a solution, it'll disrupt that pattern. All right? If the pattern of the solution is disrupted, melting will occur. And so in order to refreeze it, you now have a solution because once that solid ice starts to melt, it will then dissolve whatever substance you put on it. In order to refreeze it, you're going to have to decrease the kinetic energy. Therefore, in order to do that, you have to decrease the temperature. Are we good? So for example, you have ice in the solid state, or water in the solid state, solid ice on your sidewalks on a cold day. It's only water in the solid state. You add some sort of salt to your solid ice, and that disrupts the organized arrangement of the solid water upon contact. The ice will start to melt because it experiences increased kinetic energy among the molecules due to that disorganization. A solution is formed as the ionic compound begins to dissolve in water, and although the temperature remains the same outside, the resulting solution cannot refreeze due to the increased kinetic energy of the resulting solution. The temperature outside would have to decrease in order to solidify the solution. And next time we will learn how to do calculations for finding the new freezing and boiling points.